So this is the syllabus statement that I'm interested in for this video, but we need to understand, first of all, before we move forward, what this curve is all about. Now, be careful with exam questions, because sometimes the exam question asks you to describe the events that take place during an action potential. So what we're going to talk about, if that's the question, is that we've got resting potential set up. If there's some kind of stimulus which reaches threshold, sodium ion channels open up, sodium moves in, positive feedback, depolarization until we hit this moment, and this is when sodium ion channels are in their refractory period. Sodium ions are responsible for depolarization because they're quick to respond. At this moment, what we've got are the slower acting potassium channels, which now open up whilst the sodium channels are in their refractory state. Potassium moves out, and that causes repolarization. Because the fact that sodium channels are not allowing any conduction at all, we also get hyperpolarization. Here, the potassium, so the sodium ions come out of the refractory state, some movement, and we re-establish the resting potential because both ions are now moving through those voltage-gated ion channels at a voltage of -70, and we've also got the pump re-establishing the gradients. So that is the action potential. As different from this. This is asking you to say, how is the nerve impulse or the action potential propagated along the axon? So if we're asking for the events of an action potential, it's this. If we're talking about propagating along, what we're talking about is how do we get the action potential to move along the nerve like so. So this is the action of depolarization. Moving that charge and moving those changes along the nerve is propagation of the action potential, which is different. In the PowerPoint, I want to draw your attention to all of these resources. I would suggest you watch all of them, because the more that you can see this, especially in an animation form, the clearer it will become. I also urge you to talk aloud, try and explain aloud resting potential and action potential. If you can do those things, then you're in a good position to move on to this idea of propagation of the action potential. This comes from BioNinja, also might be very useful for you if you like visualizations. So we've got the depolarization visual here, we've got the repolarization visual, and we've got this idea of the refractory state. So now what we need to consider is this syllabus statement, the propagation of the nerve impulse. So we're talking about how does this motor nerve carry its action potential or its impulse all the way along the axon until it gets to the terminal part of the axon here. Now, remember that this part is inside the central nervous system. When we look at the synapse, it will make more sense later on, but what's going to happen is a chemical phenomena happens here, which is going to cause action potentials to be set up in these dendrites, and that action potential then is going to get propagated along the nerve in this direction. The propagation is one way. It comes from the cell body to the effector in this direction, and we need to think about what happens to propagate that along and why it's one way. This diagram here, I think, is quite helpful. What I would suggest that you do after this video is set up a diagram which is similar to this, but add more detail to it. So we're just thinking about this patch of nerve here, and this patch of nerve, I want to call this part A, and then the part adjacent to it, I'm going to call B, and then we're going to call the next part adjacent to that C here. So we've got A, B, and C, which are different parts of the axon. So imagine that the action potential is here. What's going on? Well, the nerve is going to have an action potential. So sodium is moving, and the sodium moving is going to cause sodium channels are going to respond to a change in voltage. Sodium is going to move in, and we're going to get depolarization. We're going to reverse the membrane potential at this patch of nerve here. Now, I want to look at the intersection between section A and B. What we've got here is a difference in charge. We've got on this side of the membrane a positive charge here, and adjacent to it, we've got a negative charge. So that is going to cause a local circuit to be set up in this patch of the axon here. And that local circuit, that electrical flux, is going to change the voltage across this part of the nerve, which is currently at rest. But that local circuit is going to cause sodium ion channels to respond, sodium to open up, and as a consequence, sodium moves in. So even though this part is active, it's going to cause its adjacent region to become active. So this is showing the depolarization has moved from here to here. This is time coming down here. So this is time 1, time 2, time 3. Depolarization in A causes depolarization in B here a little bit later. So depolarization, sodium moving in, but then the sodium hits its refractory state. The potassium ion channels are slow to respond. The potassium starts to move out, which is why the depolarized part of the nerve is now repolarized. So at this moment, it's all about sodium ions moving and sodium ion channels behaving. Here, what we've got are potassium ions moving and potassium ion channels responding, and the refractory state of the sodium. So that's repolarization. Here we've got depolarization. So this part adjacent, we've got a positive and a negative charge. We're going to have a local circuit set up here, and that local circuit is going to have the impact of opening up the sodium channels at time 3 in section C. So we got depolarization moving from part A to part B to part C in time. So we've also got a local circuit here. And this local circuit here is going to also cause the ion channels to respond, but because sodium ion channels are in their refractory state, they're not responding. So even though you've got an electrical event here, local circuit here, then this repolarization becomes resting because the sodium ion channels are in their refractory state. And that's the reason why the action potential, the depolarization wave, is going to move in one direction. It can't go backwards. So it can't be, this local circuit here can't cause this part to become depolarized again because the sodium ion channels are in their refractory state. So what we've got here then is a local circuit in part C, region C. We've got a local circuit here. Nothing is going to change here. It's repolarization. The sodium ions are in its refractory state. So if we looked at the next moment in time, this part is going to be back to resting. That depolarization part is going to move to the next part of the nerve. And we call this local circuit theory. Again, there's a lot of vocabulary. There's a lot of it's somewhat counterintuitive at moments in time. Try to talk this out. Try to map it out. When you're looking at past paper questions, make sure to distinguish between a question which is asking you to describe an action potential as opposed to the propagation of an action potential. I want us to come back to this idea that the motor neuron is myelinated. And if we look at this slide, the myelin, remember, is created by the Schwann cell. It's a fatty sheath. It's an electrical insulator. So when you have myelinated nerves, that allows for what's called saltatory conduction. If you look at the BioNinja animation, it's very nice and it shows you this. But what happens in terms of the local circuit theory is that you get at the nodes of Ranvier all those events which we've just described taking place. And in effect, what happens is that the depolarization jumps from here to here, and it speeds up the conduction. So you've got a local circuit being set up here, and it goes immediately to this part here. So saltatory conduction is only in myelinated nerves. Motor nerves and sensory nerves allow the jumping in effect of that local circuit from one node to the next node, speeding up the rate at which an action potential can be propagated. The next syllabus statement is a skill. Again, have a look at the BioNinja animation. It's all about looking at oscilloscope traces and looking at what the resting potential and the action potential. So we're looking basically at being able to describe this part here is becoming more positive. This is more positive because the inside is positive compared to the outside. This is because of sodium moving. It's all about looking at traces and being able to talk about what is causing these events to take place. Have a look at that. Just make sure that you are comfortable with this. There's also this PhET animation, which you can pick up the link in the Google Classroom and you can take a look at to embed these ideas. And then there's a little bit here again, which is all about this idea of saltatory conduction and the fact that we got the action potential jumping from one part to the next.